So up next, we have Salman Punekar. He's a medical oncologist and the assistant professor at NYU Promuter Cancer Center. He came down to us from New York. Yes, all right. Shout out for New York. Okay. Welcome to Charlotte. He has completed his postdoc research fellowships at the University of Pennsylvania and Yale University, where he's also completed his medical training. He completed his fellowship in hematology and oncology at NYU, where he's currently a clinical and translational investigator with a focus on early phase clinical trials for patients with solid tumors. He leads several very high impact clinical trials for KRAS directed therapies for patients with lung cancers, pancreatic cancers, and colorectal cancers. And in case you did not know, those are the three colors on our socks and where most of the KRASs are. And so it is absolutely beyond delight. I am just pleased as punch to bring you up here this morning. Welcome to Charlotte and welcome to the KRAS Kickers. I hope you are wearing the proper footwear. And if not, we may just say can't make you have to go out and do a quick change. So thank you. Go ahead.
Thank you. I can just take this. Right. Good morning, everyone. Thank you so much for having me. It's really my honor to talk to you. So as Terry mentioned, I'm primarily a phase 1 investigator. And so what that means is that I actually see almost no patients for quote unquote standard of care. And so patients come to me often referred by other oncologists because they're in need of a clinical trial. Patients see their oncologist, they get certain treatments, and then they come to me and say like, hey, my oncologist feels like my options are a little bit limited. Can you help me with that? And I'm really quite fortunate because I look at my job as primarily to give people options. And if I can successfully give somebody another 4, 5, 6 options for treatments, then I feel like I've done my job. Okay, so one other kind of thing that I wanted to add is that, about my job is I work a lot with different groups. So in addition to patient advocacy groups, I work a lot with sponsors. Sponsors are biotech companies, pharmaceutical companies, work with various research labs. And that's a little bit different than your standard oncologist who may be seeing patients all day, 5 days a week. So hopefully that will add some color to what we're going to discuss. Okay, in terms of my disclosures, I don't have any financial disclosures, but I do want to disclose that I am the principal investigator of several very high impact KRAS clinical trials. And obviously I'm part of these clinical trials because I believe in them and because I think that they are going to be the future. And then the other thing I'll say is that I'm only going to discuss publicly available data today. Just because we're not trying to get in trouble. Okay, so the agenda. I'm going to reiterate a lot of the things that Dr. Dare and Dr. Marone had talked about, but I want to do that in the context of actually inhibiting KRAS and inhibiting multiple isoforms of KRAS. We will do a little bit of science, but don't stress so much about that. I want you to really think about the concepts. And I'm happy to take as many questions as needed. I don't have too many slides, so we'll have lots of time for questions. So we'll talk about targeting KRAS, we'll talk about resistance to various KRAS inhibitors, we'll talk about Pan-Ras or multi-Ras inhibition, and then we'll share some clinical data that was presented several months ago. Okay, so targeting KRAS. So we know that KRAS mutations are important and very common across many different cancers. So you've heard this many times before. And by far, most RAS mutations are KRAS mutations. The big ones that we see a ton of and match KRAS Kickers colors are pancreas cancer, lung cancer, and colorectal cancer by far. But then there are other less common cancers that do have various RAS mutations, including KRAS, NRAS, and HRAS mutations. These are some of the key KRAS mutations that we like to talk about and target. Think about them really as the G12, G13, Q61, and then some of the NRAS and HRAS mutations, which are a little bit less common. But these are kind of the core ones that we're thinking about targeting. So the KRAS protein, it's a pretty complicated protein, but you have a mutation. So basically what happens is that your body has DNA. That DNA is the code for a protein, and that DNA can be mutated. When you mutate the DNA, then you create a protein that is misshapen or somehow different. And oftentimes when it's different, it's, as Dr. Durr said, it's stuck in that on switch. So it's a KRAS on, which really shouldn't be on. KRAS is 99% off in normal cases, but in cancerous cases, it's 99% on. So we really don't want that to happen. KRAS mutations can happen in a variety of different places within the protein, and that part is really key to our discussion today. In addition to that, when you have mutations in KRAS in the three most common cancers, you can see here, looking at just all the different colors, that different people will have different mutations. And so if somebody comes to me and says, oh, I have a KRAS mutation, my next question is, okay, what kind of KRAS mutation? And then let's be specific. Don't tell me you have a KRAS G12 mutation. Tell me you have a KRAS G12V mutation or G12D or Q61H, right? All of those nuances are really, really important for me to help select therapies that could be effective for you. This is a really interesting slide from one of my papers because it shows the cascade of RAS or KRAS. So this is kind of the way that we think about how proteins work. So proteins have signaling cascades. And what that means is that it's a domino effect. The protein does something, it hits another protein, that does something, so on, so forth. You knock all these dominoes down, and then at the end of the day, you grow a cell. And that's normal. However, if you keep doing that, and you do it when the cell's not supposed to grow, that's cancer, right? That's called oncogenesis. We can target multiple spots of this pathway. Think about a highway with several exits. We don't just have one exit. We're not just looking at the KRAS exit. We're looking at the KRAS exit. We're looking at exit 1, exit 6, exit 18, and then maybe even we do multiple of these. So this is really interesting because I just want to illustrate how far science has come. KRAS or RAS for decades, people love to say, it's undruggable, you guys aren't going to be able to do anything with this, but here we are now with a list of drugs that we know can target the KRAS pathway. So progress is being made, progress has been made, and progress will be made. The various KRAS inhibitors that we have, they're all a little bit different, right? These are their chemical structures. It's not important that you pay attention to this. My point is that they're designed differently or they're discovered differently. Generally, the way that these compounds are found is that you take what's called a molecular library. You take thousands and thousands of these compounds and you see what fits, right? So it's like throwing hundreds and thousands of darts at something. One of them sticks. You're like, okay, that's a G12C inhibitor. That's a G12D inhibitor. That's a multi-RAS inhibitor, so on and so forth. So that distinction is really important because all of these drugs are distinctly different inherently in just the way that they're created. And so when we create the next generation of these drugs, we need to keep this in mind. Okay, resistance mechanisms. We've had a lot of success, or I'll call it relative success, but that success has been modest with G12C inhibitors. We have FDA-approved options, sotorasib, adagrasib. These have led to big landmark studies, big papers, presentations, everybody's excited. There's millions and millions of dollars being put into these drugs, but they're modest, they're not curing people. They're helping people to some degree, they're helping them live longer to, several months. Response rate somewhere in the 30 to 40% range, maybe a little bit higher depending on some, newer agents. But my point is that there's still a lot of work to be done. And a lot of that has to do with the resistance mechanisms. So why is it that you give a G12C inhibitor to somebody and then it stops working? Or it never worked in the beginning? That's what we're going to talk about here. So at the top here, if you take a bunch of cancer cells, and you just kind of put them in a petri dish. We give them mutations. So we create these mutations. And then we start giving them the treatment. We give them sotorasib. We give them adagrasib. You can actually select out the ones that are going to grow despite the treatment. So this is called creating models of resistance. So this is something called a cell line study where you take cells, there's cancer cells, and you kind of artificially create resistant cancer cells. And we do this to model what happens in human beings. In human beings, this is what's happening on a daily basis in a person's body when they're being treated with a various KRAS inhibitor. The bottom part is to illustrate that mutations occur that are distinct from the original mutation. So if somebody has a KRAS G12C mutation, over time, they develop these other mutations and a lot of other RAS mutations, and this part's really important. So G12C inhibitors are selective. That means they only work for G12C. A G12C inhibitor does not work for G12D or V or R or NRAS or HRAS, right? That's kind of by definition. It has a very small pocket. We talked about how that pocket was discovered several years ago that really opened up the field to KRAS inhibition. The problem is, okay, you did that, and that's great. You blocked KRAS G12C. But now you've created these other KRAS or RAS mutations. What do you do about that? The other thing that's really important to note is that there is various resistance to different KRAS inhibitors that are not very obvious. So sotorasib and adagrasib are both G12C inhibitors. They work very similarly. But as you can see here, they don't work exactly the same. There are some mutations that you can develop that may make you sensitive to a certain KRAS G12C inhibitor or resistant to another KRAS G12C inhibitor. So this is another nuanced kind of piece here. Because patients may come to me and say, oh, you know, my doctor put me on sotorasib, it stopped working, and so my doctor said, you know, G12C inhibitors cannot help me anymore. That may or may not be true, and that kind of underlines the importance of repeating next generation sequencing. In my practice, I get next generation sequencing on anybody who comes to see me right from the beginning, whether that's stage 1 cancer or stage 4 cancer, and any time their cancer progresses or gets worse. If their cancer gets worse, I will at least do something called a liquid biopsy, which is not truly a biopsy, but it's a way to look at next generation sequencing in the blood. And I may consider doing an actual biopsy, either of a liver lesion, lung lesion, lymph node, pancreas lesion, so on and so forth. Okay, so this is a real patient. So this is from a very important paper by Mark Awad that shows resistance to adagrasib. So adagrasib is a G12C inhibitor. This is a patient that had G12C cancer. Initially, you can see on the, I guess that's the most left side for you guys. There's a lot of cancer there, and we don't need to learn how to read CT scans right now. But after several months on adagrasib, the cancer got better. Great news. But then the cancer started to get worse again, and this is exactly what we're talking about, the resistance to adagrasib. Doing next generation sequencing at that time revealed a KRAS Y96C mutation. That's really important because the codon, the part of KRAS 96, that little section, modifies the binding site to where a G12C inhibitor binds. So if you now have a G12C mutation, and now you add on a Y96C mutation to that, that G12C drug, that inhibitor, cannot even bind. So it can't stick there. If it can't stick there, it's not going to work. And so predicting this is very helpful because we can actually predict this before we even do the scans. So if we were to do next generation sequencing that shows this new mutation that arose, then we can say, like, okay, you don't have to wait 4 weeks to get your scan because we know what this is going to show. And if we can save you 4 weeks, just kind of as a side note, you'll notice that a lot of clinical studies are in increments of 6 weeks. They'll say, like, oh, somebody did better for 6 weeks or 12 weeks or 24 weeks. The reason that interval is 6 weeks is that that's usually the time that we do CT scans. We generally do CT scans every 6 to 8 weeks. And so if you can save somebody 4 to 6 weeks, that's actually a good amount of time. Here are some graphs of various patients, also from the Mark Awad paper from the New England Journal, that shows that resistance to adagrasib, a G12C inhibitor, is associated with various other mutations. And this is the key that I'm trying to drive home. we do not often see resistance to KRAS G12C inhibitors without other mutations. There's a reason why a treatment stops working, and it has a lot to do with this. Okay, so with all that context now, I'm going to now talk about Pan-RAS inhibition. I do want to just clarify, there is a difference between Pan-RAS inhibition and multi-RAS inhibition. For practical purposes, that distinction is relatively small, and I think that we can use it interchangeably for now, for the purposes of our chat. But just know that technically Pan-RAS means that a drug affects all Pan-RAS, or all RAS molecules, whereas RAS multi means that it affects multiple RAS. And suppose, you could have a drug that attacks 5 RAS. That would be a RAS multi. Pan-RAS technically would cover all RAS molecules. Okay, so the most exciting drug in KRAS mutant cancers in the past several years, in my opinion, is RMC-6236, Revolution Medicine's multi-RAS on inhibitor. This is a tri-complex inhibitor. What that means is that the drug is this little yellow thing at the top on the left-hand side. It binds a protein found in everybody called cyclophilin A. When it binds that, only then can it bind RAS when it's activated. And why is it important to bind RAS when it's activated? It's important to bind RAS when it's activated because mutant RAS, I told you, is 99% activated. It's almost always activated. So why would you target RAS when it's off? It's not the ideal way to target RAS when it's off. I don't know if I mentioned this earlier, but the other KRAS inhibitors that are approved are actually KRAS off inhibitors. They target RAS when it's off. But wouldn't it be better if you could target RAS when it's on? Because that's when it's causing problems, right? When RAS is on, it keeps growing cells, it keeps growing cancer, it causes major issues. Okay, so now that you bind the drug, 6236, with cyclophilin, and then RAS, that's the tri-complex. So those three together, that's the winning combination. That's what stops the RAS molecule from working. This inhibitor, this tri-complex inhibitor, hits all the important mutational hotspots. Q61, G12, and G13. 3 of the most common areas that we have KRAS mutations. So think back about all this resistance stuff that I talked to you about. The reason that I led my talk talking about that resistance is that suppose you start off with a G12D mutation, and you were taking a G12D inhibitor, and then you were to develop a Q61H mutation. All right, well, then you've kind of lost the effectiveness of your G12D inhibitor. But what if you were to target both right from the beginning? You would then actually prevent the development of that resistance mutation. And so that's the promise of a multi-RAS inhibitor or a pan-RAS inhibitor, is that you can prevent the development of resistance by thinking about what could happen and stopping it in its tracks. Hope that makes sense. So that's really by far the most important thing that I'll say today, is the importance of a multi-RAS inhibitor is to prevent resistance, at least in RAS. There are other types of resistance, and we can have a separate chat about that, but at least in terms of RAS-related resistance, it's very important. Okay, I'm now going to talk about some clinical data. So this is a presentation by one of my colleagues, Casey Arbor. I'm also a author on this presentation given at ESMO several months ago. Okay, so this is the phase 1 study of RMC-6236. A phase 1 study, so studies come in phase generally 1 through 4. Phase 1, safety and tolerability, relatively small number of patients. We want to make sure that these drugs are safe. We want to make sure that we understand how they cause side effects. Phase 2 studies, we do a little bit more of that. We want to see how effective it is. And then phase 3 is when we look at comparative effectiveness. So we compare it to what's currently out there. This is a phase 1 study that we started at a very low dose, 10 milligrams. We kept going up, 200, 300, 400, 500 milligrams, with the idea of seeing how much can people tolerate, At a low dose, does it cause side effects? At a really high dose, does it cause too much side effects? And you try to identify the best dose of this drug. In this clinical trial, we actually restricted it at this time that this data was presented to KRAS mutations only. The study now accepts patients with any RAS mutation, so that part's also important. R, A, S, V, and D, G12C inhibitor, G12C mutations were excluded. The reason that we did that is that there are a lot of G12C inhibitor trials out there, and so there's kind of a strategic reason not to do that, not necessarily a scientific reason. Okay, in lung cancer, G12X, by the way, just refers to G12 and then RASVD, so it's not actually a different mutation. But what you can see in this, all of the lines above the horizontal line show that the cancer is getting worse. All of the lines below show that the cancer is decreasing in size. And so from this, you can see that the vast majority of patients, their cancer decreases in size. This is groundbreaking because this drug for lung cancer has a disease control rate of 85%. Disease control rate, in my mind, is the most important thing for patients. It's a little bit not so important for clinical trials, and we'll talk about why that is later if anybody wants to quiz me on that. But disease control rate basically means what is the percentage that the cancer will stay the same or decrease. And for a lot of people, if you told them like, hey, your cancer will stay the same for the rest of your life, probably jump up and down and be thrilled about that, right? So that's why I think that's a very important number. The way that we define response, just as a definition, is that based on a certain number of lesions, so we'll take a person's CT scan, we will arbitrarily, I shouldn't say arbitrarily, we will semi-arbitrarily pick some areas that we're going to track over time. You have to show decrease in size by 30% to be able to say that that's a response. But what if you have 25%? That's still pretty good, right? What if you have 29%? That's still pretty good, right? So that's why the disease control rate is actually clinically important for patients, but may not reflect in some of the numbers that we present. The other thing that this graph shows is each of these little lines, this is called a swimmer's plot, each of these little swimmers in their lanes shows each individual patient. And the further the line goes, the longer they're on treatment. So think about it this way. Why would somebody stay on the treatment? They'd stay on the treatment because it's working, right? So the longer you stay on the treatment, the better. And then you see these little yellow dots that start somewhere in the first, close between the 0 and 6 number. That's when they first had their responses. So most patients have responses relatively early, within 6 weeks. Remember I told you that that interval is usually 6 weeks? That's when their first scan is. They have a scan at 6 weeks, they have a decrease in their cancer, and then a lot of patients are able to stay on the drug because it's effective. Shifting gears a little bit, same story with pancreatic cancer. Disease control rate now 87%, with a response rate of 20%. I'm going to ask a question. Does anybody know what the response rate for second-line chemotherapy in pancreatic cancer is? Somebody throw out a number. It's about 6%. 6%. I feel like you could, anything's better than 6%, right? At that point. Anyway, so this study showed a response rate of 20%, which is still better than the benchmark of that 6%, but the disease control rate of 87%. And one other thing I'll point out is that you'll see underneath these little SDs and PRs, there are these arrows. That means the patient is still on treatment. And so when we do these clinical trials, we do something called a data cut. The clinical trial goes on for several months, and at some point we say, okay, we're going to stop and collect the data at this point, people are still going on and continuing the trials, but we're only going to analyze the data as of, in this case, it was September 2023. So by now that we're in March 2024, more patients have stayed on study, and these numbers can change. Very similar story. A lot of patients stayed on study with pancreatic cancer in a very similar fashion. No talk about phase 1 clinical trials is complete without talking about side effects, right? That's actually one of the biggest things that we evaluate in a phase 1 clinical trial. I told you the primary point of doing one is to look at safety and tolerability. So we do see a lot of side effects. That's important because now we need to figure out, okay, we've developed a drug that we think is effective. We'd love to maximize that effectiveness, but at the same time as we maximize that effectiveness, we have to minimize the side effects. The big side effects that we presented were rash and GI issues, nausea, vomiting, diarrhea, these types of things. But there's a lot of opportunity here for optimization. So there's a lot of work that we can still do, and I'm going to lead into something to help hammer this point home. So the next wave of clinical trials will really think about how do we avoid all resistance. So Revolution Medicine has the RAS multi-inhibitor, the 6236, but they also have several selective inhibitors. 6291 is a G12C inhibitor. So suppose, walk with me on this little journey here. Suppose you were to have a G12C inhibitor. That's pretty effective. And if you give it at a moderate dose, it causes not so many side effects. That's great. But I told you that you can develop resistance. Okay, but what if you were then to use it in combination with a multi-RAS inhibitor? That might avoid some of the resistance. Suppose you were also able to use that at a moderate dose, so you're not using either at very high doses. It is possible then that you can have a very effective treatment that has low side effects. And so that's the goal of the next wave of clinical trials, is various combinations. There are clinical trials out there that will combine a KRAS inhibitor with anything you can think of. What I'm here talking about is using KRAS inhibitors with other KRAS inhibitors to get that really multi-RAS approach. All right, so I talked a lot about various issues within KRAS or RAS in general. We talked about clinical reasons or mechanistic reasons for why this approach makes a lot of sense, and we went through some clinical data. So with that, I'm happy to answer questions and chat more about this. As you can see, this is something that I love to do, so yeah.
I'm coming. Is it because you were on the opposite corner of the room? You wanted to ask something?
Yes. Oh, thank you so much. There was so much information. I have a few questions, but I'll just start with one. The first one is this. I know this isn't your primary area of research, but since you use it as a diagnostic tool and you mentioned liquid biopsies, I was wondering about that technology, where that's at right now, in terms of some of us are not shedders. So how much faith do you have in liquid biopsies, knowing that you're going to miss some people who, or what's being done to address that, or what do you think about that issue, and how do you work around that?
Yeah, I think let's explain what a liquid biopsy is. So a liquid biopsy is not actually a biopsy, right? It's a blood test that looks for fragments of DNA that come from cancer in the blood. So the problem with that is if you don't have these fragments of DNA, as you said, shedding into the blood, then you're not going to pick them up. However, if you do pick them up, then you're pretty certain that they're coming from the cancer. So if you do have it, very high positive predictive value. So we know that it's real. If you find nothing, then I actually put very little faith in it. So if I see a CT scan that shows cancer, I do a liquid biopsy that picks up no mutations, then I end up doing a tissue biopsy.
Are you aware of improvements being made in liquid biopsies? I mean, is it that it's not detecting when people are not, when they're not shedders, is it their, but do we know why? Or is it just not detectable in that test?
I think what you're getting at is how good is the test. Is that right? Yeah, so the tests are actually very sensitive. So the tests are quite good at picking up mutations. There are ways that we can actually give various treatments or actually radiation in clinical trials that will help increase the amount of shedding. So this is particularly interesting in patients who have cancer that is spread to their brains. So you can actually, there are clinical trials that will give various treatments that will allow some of that DNA to shed into the blood through the blood-brain barrier, and then you pick it up on a ctDNA test. But yes, there are ways to make it more sensitive, but that's not the key issue. The key issue is that somebody's cancer is being hidden by the immune system and is not being, tossed into the blood.
Hi, I just want to get a point of clarification. When you say prevent resistance, you don't mean that a G12C inhibitor down the road will not develop a Q, but the 6236 drug will just cover that up because it's able to bind to it.
No, I actually mean preventing resistance. Yeah. And the way that happens is that cancer clones start off very small, right? So you start off with a single cell, and then that will multiply into thousands and then millions of cells. It would bind it when it's at the single cell level. So before it's a clinically significant resistance, it would prevent that.
You mentioned that there were other resistance mechanisms for the pan-KRAS inhibitors. Can you elaborate?
Yeah, sure.
Anything?
Yeah, I will refer you to my. I have a paper in Nature that talks a lot about this. But in general, what I was getting at is that we have resistance within RAS. So these are secondary RAS mutations, and that's what using multiple RAS-targeted drugs can help with. And then you have other resistance mechanisms. So you can actually develop EGFR mutations. You can develop actually even a change in the cancer from an adenocarcinoma to a squamous carcinoma, these types of things. So there are a lot of different non-RAS related resistance that would not be combated by this approach.
Are people being included that have, they started out with an EGFR or something and then they acquire a RAS mutation?
Yes. Yeah, it is. It's tough, right? So when you do a clinical trial, you have to think about it from the perspective of you have a drug that you believe is effective. You want to get it out there to as many people as possible. And so the way that you do that is you convince the FDA that your drug works and that it's safe. So that's the whole reason for these inclusion and exclusion criteria. You select a group of patients that you think are going to benefit the most so that you can do it in a small number of people. You can only expose 20, 30, 100, 200, 300 patients, whatever your sample size is, to the drug. Demonstrate effectiveness, go to the FDA, then go to the next step. So selecting a patient in the beginning who has an EGFR mutation with a developed KRAS mutation is probably not the best way to demonstrate effectiveness. But yes, as of now, we are accepting those patients.
Yeah, my wife was one of the pancreatic 6236 initial ones at 120. And I lost her back in May
of
last year. But she was doing extremely well with the drug. She had 2 spots in her lungs that eventually started mutating and that's what took her life. It wasn't the pancreas cancer part of it. But when we went into it, they said, okay, we can't treat the lung part of it, is there a way, or they're going to start looking at, okay, if you have a metastasized someplace else, to address that while you're still doing with the trial drug?
Yeah, this actually gets back to Dr. Marone's point where she talked about doing optional, quote unquote, optional biopsies. A lot of our protocols have the option of doing a biopsy at progression. So that means that if the cancer gets worse, you do a biopsy. I actually strongly encourage patients to do that because not only does it help us as scientists and clinicians and the field, but it also helps patients understand why did their cancer no longer respond to the drug. So, we talked about different resistance mechanisms that were not RAS related. My guess is that in your late wife's case, something like that was going on.
And I just did wonder if they would take and, treat with radiation or something, those 2 spots in the lungs or whatever, in addition to doing the trials or things like that. I know it might be out of the perspective of everything.
Yeah, that's actually a tough thing that we always have chats about with patients is that, you have to kind of think of it from the perspective of when you go on a clinical trial, a big portion of that, in addition to hopefully benefiting from that clinical trial, is to generate data. You generate that data that can help support the development of further trials. And so if you end up using 2 treatments at the same time, then it's hard for you to go to the FDA and say, no, actually, the drug did this, right? Because then the FDA will say, no, you did radiation, so maybe your drug does nothing, right? And so trying to avoid those types of situations. So that's why we tend not to allow multiple treatments at the same time.
Are you, for metastatic colon cancer, is there any clinical trial data on that, or is that something that might become irrelevant? Because I just saw the non-cell lung and
it's forthcoming.
pancreatic.
Yeah, it's forthcoming. The reason for that is that when we did this trial, we enrolled mostly pancreas and lung, but there are patients with colorectal cancer on this clinical trial. Their data has not been released yet, though.
Okay.
Do you have any dates that you can share? Were you going to be presenting anytime in the future?
I cannot share. I'm
Okay.
sorry.
Okay. No, that's okay. It's okay.
Yeah, please don't buy or sell stock based on what I say.
Yeah. Yeah. Well, no, and sometimes it's like, I know that they embargo the data, and so there's nothing that's come out. But sometimes it's like, I know the AACR stuff's coming out soon. So.
My question is about who is represented in these trials. I know we all know that there are underserved populations and there's some that underrepresented in trials, right? I wondered who you see. Is that something? Are there efforts on NYU's part and your part to serve more people? And I'm just wondering about the kinds of populations you are seeing.
Yeah, that's a really important question. And I'll tell you that, one of the sad realities about clinical trials is that most people who end up on clinical trials are the ones who advocate for themselves. And so that means that you're pretty savvy. So everybody in this room is savvy. I'd consider you in the top 1 percentile of all patients. But what about everybody else, right? And so what we do at NYU, to answer your question, so virtually all of my patients are referred to me by somebody else. But we work in very close partnership with the New York Health and Hospitals system, which is the safety net hospitals within New York. So these are patients who are underinsured or uninsured. And actually, NYU doctors go to these places. So we staff those places. And because we do that, we are kind of intricately involved in the cancer centers there. We are able to get those patients referred for clinical trials. And the reality is that these are patients who, we have to talk to them about what a clinical trial is. Whereas folks as yourselves, you've already done that work and coming to me asking for the clinical trials. We go to these folks to try to improve representation.
Do you take any sort of video visits for second opinions?
I do. One of the restrictions that we have is that we are only allowed to do video visits in states that we have medical licenses. And so I only have a New York medical license currently. And so I'm only allowed to see patients in New York.
Kevin, And just so you all know, too, on the KRAS Kickers website, we have a list of clinical trials that are KRAS.
Sure. Does having brain mets disqualify you from most trials?
Having active brain metastases disqualifies you. Yeah, I'll explain. So an active brain metastasis means that it's a brain metastasis that has not been treated and is not stable. So generally what we do, and I'll explain the reason for why we do this, is that if somebody is found to have a brain metastasis, they get radiation to their brain, they wait 14 to 28 days, make sure that the brain metastases are not growing, and then they go on the clinical trial. And the reason for that is that not all drugs go into the brain very well. There's this thing called a blood-brain barrier that prevents particularly large drugs from entering. One thing that we have done in other drugs, so sotorasib and adagrasib, is that we've specifically given them to patients with brain mets before they got radiation. And that was in part to see how well it transferred into the brain. That is restricted to patients who have what's called asymptomatic brain metastases. So they had an MRI, it showed something, but they weren't necessarily feeling headaches, blurry vision, or trouble walking, things like that.
Do you have any sort of like ongoing studies that you're aware of that include brain mets, like maybe, or you foresee something in the future coming, maybe with this or with other treatments?
I can't comment on whether that's coming for 6236, but for G12C inhibitors, they currently are enrolling patients, yes. There's actually data presented for intracranial response with sotorasib last year.
In that paper you talked about from Marko Wadzoff with the G12C, I know that, and if anybody is here on a G12C, if you have progression on a G12C inhibitor, they will for free take your blood and they're tracking it. So you can be included on it, and we have that information as well.
Yeah.
It's called the SPARK protocol.
Yeah, that's a good point to bring up. You know, almost every institution will provide these types of services entirely for free. And so if there is a situation where you feel like you want a biopsy and your insurance company is not covering it or anything like that, we can certainly do that for you at pretty much any major institution.
Yeah, and okay, you had a question?
Is there anything currently for early stage, stage 1, that is for recurrence, to prevent recurrence?
There are some of the vaccine trials that Dr. Marone talked about to prevent recurrence after stage 1. Are you referring to lung cancer?
I had surgical, stage 1A.
Lung cancer, though? Yeah. Yes. Yeah. So there are vaccine trials. One thing that is interesting is that we know that there's a very big difference between stage 1A and stage 1B. So generally from stage 1A tends to be on the much milder side in terms of chance of recurring. And so it actually becomes very difficult to study preventing that. So if you have a 70% chance of the cancer not coming back, it's actually a lot harder to study because then you have to put thousands of patients on to see if it decreases it. If, however, you're talking about stage 3B, 3B has a 70% chance of the cancer coming back. It's a lot easier to study. So in a small number of patients, you can demonstrate that a vaccine can decrease that chance. But yes, there are studies, and there will be more.
Hi. Are you running any like T-cell trials that you can share any information on, and if they're, you know, how they're doing?
I cannot share how they're doing, but yes, we have various CAR T-cell trials and TCR trials at NYU, some of which are KRAS specific and some of which are against other antigens. I think that that's probably a very interesting area of study and an area of study that I lead personally. And I think it's certainly worth your while. So having said that, you know, we talked a lot about biomarkers and next generation sequencing. The other thing I'll add to that is that really everybody should have HLA typing. HLA typing is your, like, you know, people have ABO blood types. This is like the next level. It's like fancy blood typing. It's the type of stuff that they do for bone marrow transplants. We are making a big push as a field to get that standard of care covered by insurance companies, like right from the time of diagnosis, because it really opens you up to all of these various trials.
Isn't HLA something you can do by saliva as well?
Yes, you can do it in a mouth swab. You can do it by blood, both of which are simple and easy, yeah.
Yeah, I think at one point, I think it was NCI had a study out for, they would, again, it was like an NIH study maybe, it was like they would HLA type you for free, where you just spit in the tube to see if you're going to be able to qualify for it. And I see things that are coming specifically to G12V with HLA, and there's some other things as well. I don't know my own HLA, so this is, I mean,
yeah.
The last time I did biomarker testing was last recurrence 3 years ago, so.
Yeah, so we do HLA typing for free as well at NYU for anybody who comes. But obviously that means you have to show up, right? So if you can do that at your home institution, that may save you a trip if you are or are not eligible.
So if I had HLA typing, what kind of thing would it say? Is I'm HLA positive or HLA? What would it say?
So there are six levels of HLA typing. We restrict our clinical trials based on A, B, and C. And it's basically a way in which we design the T cell. The T cell is designed in a way that's HLA restricted. And so what that means is that you have to have HLA A something, HLA B something, or C something. So depending on what you have, so your report will say HLA A, as an example, A0201, HLA B, 0802, HLA C 1101, something like that.
So it'd be either HLA-A, HLA-B, and that's kind of like what we're looking for.
Well, everybody will have all of them.
Okay, and
Everybody will
so
have
we're
an
looking
A, B,
for the
and C.
specific type we have
Exactly.
underneath it. I got you. So
Exactly.
it's a subtype same ways, like G12D is different than G12C sort of a thing.
Correct, yeah.
That's what we're kind of get
Correct. Yeah.
to. Oh,
Yeah, and HLA is something that's inherited from your parents, and so you realize you have two of each. So you have 2 A's, 2 B's, 2 C's.
Are you familiar with Frontier Medicine's FMC 376? I think it falls into this Pan-Ras.
I'm not terribly familiar, no. I apologize.
Another question. I've had 4 primary cancers, and right now I have cancer of an unknown primary that was identified through biopsy with the KRAS. Would I ever be eligible for a trial having had so many primary cancers?
Unfortunately, unlikely. And the reason for that is, imagine with me if you were the FDA, right? And I enrolled a patient who has a lung cancer. And I said, all right, this drug killed their lung cancer completely. And they say, well, wait, this patient also had melanoma. That melanoma came back. Or somebody had breast cancer. Or in the other way, suppose somebody is doing really well on treatment, but then their other cancer, which is not targeted, comes back, and they end up not doing so well from that cancer. Then it really affects the data.
So establishing what's happening to the FDA is really a lot of what it is, and how narrowing down the focus of like the different cohorts for the different levels of clinical trials is so important.
Yeah, you really have to keep in mind. So in the U.S., we work with the FDA. In Europe, it's the EMA. These are really the regulatory bodies that are designed to help ensure that the drugs that are available are actually safe and effective. And so, they have good intentions for doing all of the things that they do. But there's a lot of back and forth between us and them, and we try to talk to them on, what we think. They tell us what they think. I think Dr. Morone had talked about how pneumonitis is often excluded. So patients who have had, a reaction in their lungs are often excluded from clinical trials, because then if they've had it before and then they develop it again, you may potentially kill a drug that's effective for thousands of people in the future because of this thing that may not even have been related. So that's really what you want to think about, is the population-based.
Yeah, because all these
approach.
things go back and forth. And just for, I'm going to be, hang on, but for the patients, they have the Oncology Center of Excellence. They have listening sessions that the FDA does too. And these are also opportunities for us as patients, as advocates, to be able to share our voices and what have you. Okay.
Will a company like Revolution help this gentleman with like a compassionate use if the data comes out more? Maybe he'd be able to get this off trial.
So I'll tell you that Revolution Medicine has a policy against using what's known as compassionate use medications. There is a reason for that. I'm not saying that I agree with this reason, but the reason that a lot of companies will choose not to utilize that program is that there's a lot of there's a lot that goes into these companies. There's a lot of money. Stocks are being traded. God forbid something were to happen to a patient that was treated compassionately, then that could negatively affect their entire program.
It's crazy how much you have to not just justify it, but literally stand on that patient's profile in order to get a compassionate use. It's unbelievable. Okay.
Okay, I have a question. I wanted to follow up on a question that was asked earlier, and I'm not asking for myself. I want to make that clear, or asking to put you in an uncomfortable position. I'm just wondering about the televisit. I've heard of this, I'm aware of this policy that you can only take people who are in the state you're licensed in. How do we know where people are? What if someone is temporarily located in New York?
Yeah, the patient has to be located in the state.
How do
At the moment.
At the
Yeah,
moment.
yeah.
So you could be temporarily located in New York.
You could come to Rochester, New York, and see me. Yes.
Okay, just thought that was a
yeah,
point.
but I did mention the whole televisit thing, but I do want to be clear. Myself and my staff are available to patients actually internationally. And so what we'll do is that we will chat with patients and we'll have video calls and all of those things. That doesn't mean that we're doing a formal visit, but we're talking about the clinical trial options that are available. And so there's a lot that we can do, and that's usually enough to decide if it's worthwhile for somebody to make the trip. Unfortunately, New York City is not a cheap place to come to, even for visiting and staying for a treatment, and so we really want to make sure that it's worth it before we ask somebody to do that. But I actually see a lot of international patients on clinical trials.
Okay, any last question? Otherwise, we'll just wrap it up so we can move on. Okay, cool. Thank you so much for
Yeah, my pleasure.
participation.